And so now we'll talk about the uniform continuity. So again, I talked a little bit about when we were reviewing for the exam. In general, when discussing continuity, delta depends on epsilon and let's say on the C, on the C at which you were trying to establish continuity. We were proving whether or not, like say, i.e. we proved, say that a function was continuous at a point C, and if the function was continuous on all points of C, we said the function was continuous at all points of C of a set, let's say of a set A. We said the function was continuous on A. So if we check somehow those continuous all the points of a set A, and we kind of looked at each specific pointer, if we could somehow do that and then find that there was continuous, we said it was continuous on A. And so now we have something a little bit more called uniform continuity, which says when we're finding our delta, unlike before, it's going to depend not on epsilon and C, but just on epsilon. And so now this is the way it's generally stated. And so let me do this 5.41 definition. Let A be a subset of real numbers. And let F be A to R. We say F is uniformly continuous on A. Now, again, we're kind of talking about the whole set. If for each epsilon greater than 0, there exists a delta greater than 0, such that if X and U are in A are any numbers, satisfying X minus U less than delta, then F of X minus f of u is less than epsilon. So it's going to be uniformly, again, when we talk about uniform continuity, it's always going to be on a set, you know, on say the whole set E. And so you have to be able to pick an epsilon and say, excuse me, given any epsilon, there exists a delta greater than 0 such that if x is from x and u are in A, satisfying this, then this is less than epsilon. So let's go back to our favorite function, 1 over x, since that kind of is helpful to illustrate a lot of these ideas. So let me take, I don't know, let's just pick, say, something, let's just maybe consider f of x equal 1 over x. But let me pick a specific interval, let's say on, say, 0.1 to 1. Show that f of x is uniformly continuous on this set. So now again, you have to pick you're given an epsilon, and it has to work. The epsilon you pick has to work for any point in this interval. So keep that in mind. Once again, we'll sort of do some scratch work. Again, if you can jump right to the proof, that's fine. I like to kind of scratch just to get some ideas what's going on. And so here we're going to say, again, the idea is, and it kind of relates to something I did talk about before. For something to work, if we're given an epsilon, for something to work for all values here, we're going to have to make it work for the maximum value in this interval. So, so for uniform continuity, find maximum value of f on the interval. You might want to kind of think that, and of course that's going to be, since it's going to be increasing, it gets smaller, that will be f at what, 0.01, huh? That's going to give us the largest value on the interval. And so it's going to be 1.01, and with that could be 100, huh? So keep that in mind. And so once again, again, this is still the scratch work, let epsilon be greater than 0. Again, and we want this, this to be able to work for any two values on the interval. And let's see here. So what are we going to have to do? We're going to have to say, again, we want this less than our epsilon, and x minus 1 over u. We're going to have to do it this way. Ux, sorry, we'll have to make a common denominator, just realize that. Ux, so make a common denominator, sorry. So I just multiplied this by u over u, this by x over x, and then we'll go u minus x divided by ux like this. And then we could say, we want this now, we could say this is going to be less than or equal to u minus x over 0.01 times 0.01, like this. And then we want u minus x. And what is that going to be? 1, 2, one more, like this. And then we want this to be less than epsilon. And so then we'll do u minus x is going to be less than or equal to 0.0001 epsilon, like this. And then this is going to be our delta. Sorry about that. I was thinking about bounding the function. I messed that all up. So yeah, because of course, I had bounding in my mind, but we're still looking for the u minus x, so we had to kind of go through here. And so let's do the proof. Let epsilon be greater than 0. Choose delta to be 0.123 epsilon. Then for all u and x in A such that u minus x is less than epsilon, we have 1 over x minus 1 over u is equal to ux minus x ux equal to u minus x over ux. And now this is the key step right here, is because this is always going to be less than u minus x times 0.01, and then this is always going to be less than delta 0.01, and that's always going to be less than this thing up here, 0.001 epsilon 0.101, which is equal up like that. Sorry about that. For some reason, my brain was thinking towards putting bounds on, but we're still doing continuity. So any questions on that? Now, again, so see, this was the key step right here, is that, and we'll get to do it next time. But see, we couldn't do that if our interval went down to 0. See, if our interval went down to 0, there would not have been a number that we could put in here to say for sure that that's less. And we'll talk about that next time. For some criteria for non-uniform continuity. And let A be a subset of the reals. And let F be a function from A to the reals. Then the following statements. are equivalent. F is not uniformly continuous. On A. So these things are kind of equivalent statements. It's not uniformly continuous on A. In that there exists an epsilon not, or you can just call it epsilon. Let's just see if such that for every delta greater than 0, there exists X and U in A such that X minus U is less than delta, and f of X minus f of U is less, it should be greater than or equal to epsilon naught. So again, for uniform continuity, remember we said for any epsilon, there's a delta such that for any X U in A such that X minus U is less than delta, this would be less than epsilon. So if it's not uniformly continuous, then you can find an epsilon greater than 0 such that no matter what, so and then whatever delta you pick, you can always find an X and U in A such that even though you bound X minus U less than delta, f of X minus f of U is going to be greater than that epsilon. And there's another, and once again, this sort of goes back, I'll show the picture again in a minute. And now another equivalent statement, there exists an epsilon not greater than 0 and 2 consequences X, let me ask you, let me call this X naught and U in A such that the limit as n goes to infinity, X, this should, let me make this xn, sorry about that, xn minus xun. The limit is 0, and f of xn minus f of un is greater than equal to epsilon for all n in n. So what this is saying, so it's kind of related to what we had before for uniform convergence. Whenever any 2 points are close together, the f of X minus f of U is supposed to be less than epsilon. But if it's not true, again, you have this. And what this is kind of saying, if you have 2 sequences that their limits are pretty much the same, because the limit when you take the difference of the two gives you 0, if that's greater than epsilon, then it's not uniformly convergent. So this is kind of the way they often state things. They'll say these statements are equivalent, it's not uniformly convergent, or this is true, or this is true. And once again, for this second statement here, this is probably one of the most relevant, is again, the idea is, and again, our favorite example is 1 over x, is that again, if you pick, I guess I showed this the last time, if you pick an epsilon, you have your function minus epsilon plus epsilon, and then you say you pick a delta, and yeah, the delta, let's say for point C, and that's probably in the wrong spot, really. I guess that was probably okay. I guess that was okay. Say C minus delta. And this. This is S. So if you go with a C minus delta, a C plus delta, everything will map within F minus epsilon, F plus epsilon. But if you move somewhere back here, you'll need a much narrower delta that'll work. And that's the trick for uniform continuity. There, you have to be able to find the delta that works for any u and x given an epsilon. And so whatever epsilon you pick on this function, 1 over x, you're always going to be able to go closer to 0 where you can't find the delta that'll work. And we'll kind of do some numerical ones later on, probably after the exam. Any question on that so far? And so let's do another uniform continuity. Let I be a closed interval. And let F go from that interval I to the reals. And it's continuous on I. Then F is uniformly continuous. So if F is continuous on a closed interval, then it's going to be uniformly continuous on that closed interval. And remember, that was the problem before. And remember, we talked a little bit about if a function was continuous on a closed interval, it was bounded. And so if it's bounded, then you can eventually find, for any given epsilon, you can kind of just take the worst case and find a place where this will all work. And we'll do some number problems a little bit later. So if it's a closed interval, it's going to be uniformly continuous. And let me see a couple of other things. Yeah, let me actually jump to an example here. Let me do this one here. show that f of x equal 1 over x squared is uniformly continuous. On this interval. But let me see what the best thing to do it. Yeah, but it is not uniformly continuous. The interval 0 to infinity. So take a look at that. So once again, we do some scratch work. Again, what we want, we want this f of x minus fu equal 1 over x squared, 1 over u squared. And we're gonna eventually want this to be less than epsilon, right? And of course, what we need to get out of here is like u minus x. So that's what we kind of gonna have to bound. Remember, again, we want this, what we're doing here, we want this, and maybe let me put it here. Want this less than epsilon, that's the goal. And again, remember what we want to do is we want to bound x minus u. That's kind of the goal. We want to make this less than epsilon by bounding x minus u. So let's do the usual stuff, make a common denominator. So u squared, x squared, u squared minus u squared, excuse me, x squared, u squared, and that's going to be equal to u minus u squared minus x squared. This is not too different than what we did the other day, but it's good to kind of keep seeing the same concepts again and again. And now right here, we want to sort of try to find a bound on this. So the worst, let's see, the biggest that this can be on this interval 1 to infinity, if you look at this denominator here, the smallest that's going to be is 1. Of course, anything small in the denominator makes the whole fraction big. So we want to pick the smallest possible denominator. And so we can say this can be no smaller than 1. So we can say that this is less than or equal to ux squared divided by 1 squared, right? Because neither of those can be smaller than 1. And then we're almost there. Remember, we want u minus x. And then we can just factor this x. How do you want to say? U plus x, u minus x. And divided by 1, it's just going to be 1. And now let's see. This one won't work because we can't bound this, can we? So we have to try it another way. So we kind of go through this and see, okay, this is the way we would usually do it, but we get to this point and say we can't bound that. So let's try another way. See, because here, now, if we had had, if this upper value would have been like some real number, then we could have put those two real numbers there. And then, but here we don't have that, so we're gonna have to try a different way. So that's the way you, how you kind of always have to approach these things. Try one way and say, okay, that's not gonna work. And this, again, this would be the usual process. So now let's try a different way. So let me put won't work. But again, always keep this kind of process in mind. This will often work. And then, so if this doesn't work, let's try something different. Try x squared minus 1 minus u squared. And this time we'll try factoring the fractions, huh? Let's see if that'll work. 1 x, 1 over u, 1 x, 1 over u, like that. And just let's just double check, see if that works. 1 over x squared, 1 over xu, 1 minus 1 over xu, and minus 1 over u squared. So it looks like that works. So now let's see what we can do here. Once again, we want to bound this over here. We're gonna need to come up with an x minus u again. So let's do a what could we do? Like do a common denominator again. If we do u over ux minus x over ux. And then, again, keep our 1 over x, 1 over u. And u minus x, ux. Like this. And then let's go 1 over x, 1 over u, like this. And now let's see if we can bound this here. And so now we have a thing we can actually bound, because once again, the smallest value that the denominators can be is going to be 1. And so we can say this is going to be bounded by 1. That's going to be 1 times 1. And same thing over here. One plus 1. And that's going to be equal, what, to 2, huh? Less than epsilon. And then from this, we can end up getting our delta, huh? So u minus x is going to end up being epsilon over 2, huh? So that's going to be our delta, isn't it? So that'll be our delta. Now, one thing really important, and this is where you have to be real careful, like we could not have, whenever we had a difference of these two, we couldn't have inserted the 1 here, right? Because anytime we're subtracting something, we can't be sure, you know, we can't just put numbers in here. The reason we're able to do it over here, see, we had to get everything that had just positive terms in the denominator, and that up here we were kind of just adding things. So that in that case, we're allowed to say, okay, we'll put the minimum here like this. Any questions so far? And so again, let's then do the proof. And let epsilon be greater than delta, and then epsilon greater than 0, set delta equals epsilon over 2. Then for all u and x in A. And again, you can put you don't have to put this in. A lot of people don't put that in. They'll just jump to this x minus u less than delta implies f of x minus f of u equals, and you don't have to really put, if you did the scratch work, you can kind of refer to it. And what I'll do, I'll kind of just put some of the steps in. And then this equals, what did I have here? U minus x over ux, 1 minus x, 1 plus u. And then we said that this was all less than 2 u minus x, like this. And then this is, of course, when you have an absolute value, x minus u is the same as u minus x. And so we'll say that this is less than 2 delta. And then that's 2 epsilon over 2 equal epsilon, like that. So that's often the way you kind of have to approach something like this, is that you kind of usually start with something like this. Say, okay, can I try to bound this here? You know, u minus x, it didn't work. And then, okay, maybe try a different way. So we went down here and bounded this. And then that one worked. Any questions at all on that? Any questions at all? Okay, let me do one. So the other part of it says that it's not uniformly continuous. Part 2. We said 0 to infinity. And now what we're going to do this time, we're going to use that limit criteria with the sequences, where we said that there exists, I'm going to try to use this one here. We said there exists an epsilon greater than 0 and 2 sequences such that the limit of the difference of 2 is 0, but yet this will always be greater than epsilon for all n. So let's see, take a look at that. And so, and now let's consider this. Consider the sequences x equal 1 over, let me call that x. And you can name these whatever you want. And un equals 1 over, let me make this a square root this time. Square root of n plus 1. And note that Note that the limit is n approach infinity of 1 screw to n, 1 screw to n plus 1. And this is something that we have to do if you want to disprove something. And you have to kind of have an idea what to pick. This time you don't really have any scratch word. You just kind of have to think of something that'll work. So here the limit is 0, and you can check that, or you remember from course from calculus, this is going to go to 0, and this is going to go to 0, and of course the difference is going to go to 0. So the limit of those two go to 0, and then notice that these sequences are in B, and that's one of the other criteria. Because they're always going to be greater than 0. And also, what this one's going to always be a little bit smaller than this one. So that's the difference is always going to be positive, because the denominator is always going to be slightly bigger here, always going to be positive. So all the members of the sequence are going to be in here. So now let's choose epsilon to be equal 1/2. Then let's go through our stuff. Then if we put, let's say, fxn minus fun, what does that mean? We're going to put into our sequence, we're going to put these two, un like this. So I'm going to put the sequences, these two sequences, each of them into our function. And then that means that's going to be 1 over the square, 1 over 1 over the square root. And those are squared, sorry, our function was squared. 1 over 1 over n squared minus 1 over square root of n plus 1 squared, like this. And then if we square this, that's going to be 1 over n. So that's just going to be n, And if we square this, is going to be 1 over n plus 1. So that's going to be n plus 1. And this is going to be 1 equal 1, which is greater than epsilon. So we were able to find two sequences that the difference of the limit was 0 over here. But when we put those sequences into our function and took this difference here, that was greater than this epsilon we picked, which was 1/2. And notice this is always going to be 1. So, no matter what you try to do, this is always going to be 1. It's not going to go to 0. So that's one of the ways to determining something that was not uniformly continuous.